Это первое. Сегодня Баранов Дмитрий Сергеевич, как вот по плану. Вот 3 доклада завтра будут отсутствовать. Но ввиду того, что люди не приехали, снимаются эти доклады. Но, как мы обещали, вот те, кто имеет постерные доклады, по 10 минут будет дано краткая презентация для тех, у кого только постерные доклады. Все, спасибо.
10 минут на каждый.
Да.
Ну, наверное, мы начнем. Вот я, правда, хочу воспользоваться правом ведущего и рассказать о том, что мне позавчера звонил глубоко уважаемый Николай Владимирович Самсоненко и сказал, что он, к сожалению, не может приехать, хотя старался, и просил передать привет и поздравления всем участникам конференции. Теперь, значит, первый докладчик Боб Гринье. Он сам озвучит. Please.
Okay, so I didn't know what I was going to do for you guys until last night.
Bob, slowly, please.
Okay. And what I decided was to produce something that has no formulas. So sorry for those that like numbers.
Дима, дай ему микрофон.
Да он хорошо говорит.
Ничего дальше там не слышно, это вам.
Can you hear me? Okay. Can you hear me now? So I didn't know what I was going to do, but I decided to do something that's very picture oriented. Then you can just get it. I don't know whether this is right, but you can judge it for yourselves. So I'm calling it seek and share and seek and share and seek and share. Because if you find something and you don't share it, you could just die with it, frankly. Or, you know, you might think you may make some money out of it, but then you don't. You need to share, because we're at the early part of this story. We might think we're far way through it, but we're at the early part of the story. And it's much faster, we found with our project, to share stuff, because you get 100 people, 1,000 people coming back to you with research papers and insights which you couldn't possibly have the resources to fund. And you move faster in your research and you have all of the knowledge that you've gained and all of the colleagues have gained, and you can seek again. Seek, share, seek, share. Okay, so representative of the Martin Fleischmann Memorial Project, and let's get to it. I'm going to say thanks to all these people, not literally, but I'm going to say that first, because in case I run out of time, I don't want to not say it. Okay, so don't tell nature what it is, let nature speak to you. Francesco Piantelli told me that in January 2015. The presentation will be focusing on the work of 5 open experimentalists. Suhas Ralkar, who produced the Echo family of reactors in India. Lion, he calls himself Lion, who produced the Lion family in UK. John Hutchison, the Hutchison effect in Canada, and Kenneth Shoulders, EVOs from USA. Sadly, one of those is not with us. So this is the foil generator, which is part of the reactor components for Suhas Ralkar's reactor. This is well documented. I haven't got time to go into it. You can go to our site. It's extremely well documented how this produces its foil, but essentially it produces foil that goes into the reactor. You can see a little bit of flashiness there, and here. That's the plasma discharges. Now, I shared this slide in Copenhagen more than 18 months ago.
Bob, may I ask you some questions connected with the first picture, because nobody knows the parameters of this reactor.
It's all well documented online. If I have to go through every single experiment I've got here, we'll never get to what I want to say. So if you want to talk to me in the round table and have all of the precise details, I'll do that then. So I shared this in about 18 months ago, and I asked people what can they see. It was on a foil. These fragments had fallen off the anode onto the cathode deposit, and most people see this. I don't know why, but they do. I call it the baby. And here it is blown up, and here's a couple of examples of something similar, just visual recognition. But the adamant those are the closest because you have the discharge going in. This is made of nickel, and it's a similar structure. Anyway. What I actually want you to look at is the bit at the center. So you have the Schauberger spiral, another guy that says look to nature for your answers. And it comes round and in and round and over, and boop, there's a perfect cube. No one spotted that in 18 months, and I keep asking them to look. I don't know whether it's me or whether I see things I want to see, I don't know. So Matthew 7:7, ask and it shall be given to you, seek and ye shall find, knock and it shall be open to you. It's the seek bit here, found a phrase with seek in it. Kenneth Shorter said, it is so easy not to find stuff, and you won't even know what you haven't found. So most of this work is done with a couple of tools.
Человек цитирует Библию, и дальше вот
Ищите и обрящите.
Ищите и обрящите.
A macro camera lens and a 70. It's a 2012 camera. And I can show it to you after. It's a little microscope. I'll get it out, but I'll show it to you afterwards.
Ну, есть такой уникальный микроскоп, который, говорит, 60 евро стоит.
So this is a microscope attachment for phones. It costs $60. It puts onto my smartphone there. It gives you calibrated images and videos in high definition up to a magnification of 400 times. So a lot of the images you're going to see have come from that $60 device in addition to your camera.
Ну вот прям на этот самый телефон насаживаешь, и можно...
This is something everyone can use, and this too, to look at things in cheap ways. So the line experiment, I'm going to explain very quickly how this was done because it helps to understand what you see at the end. Diapads from 3M, they look like this under that camera attachment to my phone. And these are industrial diamonds in a nickel pad. Okay, so they're doped diamonds. What are doped diamonds good for? Very good electron emitters. Okay. Those were taken off the pads, cleaned, oven baked for 200 degrees C for 1 week in this camping pan. And then they were dumped for a month into deuterium straight from the oven. The reactor was a little bit silver foil, alumina, and double wound of copper. It's not connected to anything, actually did connect it to this bolt. Bit of Parkhomov sealing, thank you. And a bolt at the end there. And the fuel goes inside, which is those baked and soaked diapads.
Нет, но у него отличие, Боб, just a moment. У него отличие, они фольгу туда вставляют. Ни мы, ни Пархомов фольгу не вставляем.
So, heated in a looking for heat tube furnace. The controls on one side, it's just a split resistance with Cantal. It's not great, but you know, it does a quick test thing, and that's what we want. There's some explanations there. You'll be able to have the presentation, so you'll be able to know what that was. The key thing here was I discussed this yesterday. He turned the power off, and then he attached to the bolt at the end and to what he calls a drain this exact light bulb, 12 volt, 20 watt light bulb, and it lit for 30 minutes, so 10 watt hours. That's with the power turned off to the device. The very interesting thing for me is this description he gave me. There was a sudden crackling sound. It sounded like a cross between scrunching up a crisp packet and the sound made by one of those large plastic storage bags when you place your clothes in over the winter, seal, and then it goes, sucks the air. And air was sucking into the tube. Into that tube furnace. So you got the tube furnace here, the reactor was in here, this is just a thermocouple, and it was going sucking the air in when he connected that. That's what he sent me. This is the reactor, so you can see what happened to the copper as it got into the heat. This happened. became very brittle. And it's actually Cu2O. So, and the suggestion is that this bulk transformed very, very quickly. Now, I'm not saying it wasn't already an oxide, but when you look at it under the SEM, and this bit is an SEM image of this section up here, it's completely glassy. Completely glassy. And so for that to have occurred, I started saying that, you know, Piantelli taught me that this has to occur at like 1,000 degrees a second drop. You do melt spinning and these kind of things to achieve this level of glassiness. And I put that out there, and someone who works with Lion said we couldn't explain this data that we recovered off the data disk, the SD card, but it shows that it went from 800 degrees or a little bit below 800 degrees to 0 Kelvin, like a straight line. So, I don't know.
Ну вот этот оксид там меди, то он в виде наплывов там
Микрофон скажи.
наплывы он видно только.
Okay, now I did this SEM, and then I went somewhere for 3 weeks, and during my being away, Alan Goldwater, MFMP collaborator in California, said, what's this? And I thought, oh damn, glad I took a lot of reference pictures when I put it into the scanning electron microscope, because we got what I consider one of the best images of strange radiation ever taken. And we have this extremely high res, and I can show you, and it actually shows you the structures of each of what I call the paw prints of the lion.
Скачки сравненного излучения, следы.
Они называют это следы льва. Видите, это похоже на лапы. Похоже на лапы животного. Следы льва.
So it's not just showing two lines, it's not showing a zigzag, it's precisely showing the shape of the paw prints. These are kind of normally what you see, these kind of tracks. This was on the inside of a previous reactor. And there's these two spots here. Now I got this after something else. I can go and zoom into here, but there's shoulders-esque type boring through the quartz, which was outside the reactor tube, and then you've got another strange radiation track on the Fisher line on the fused quartz.
Once again, show us in which place of your reactor the Lion
Here,
X.
it was in the Cu2O, outside of the core of the reactor.
Inside.
No, this is the alumina, the fuel's inside the alumina, and this is outside in the copper wire that is converted to Cu2O. 100% outside. In this case, not this case, that's inside of the reactor. Here is where the copper oxide is now, and this is the quartz liner tube that you saw in that tube furnace, and this is right on the outside edge. So this is beyond the copper, it's gone through the metal and it's now going through the quartz. And in fact there are some things out here and even further out. Actually that's a video, it's quite nice. Maybe I'll show you. You can go right and see the zigzag there. Okay, so he got this souvenir tea can. He's quite inventive. He's a bit like you, Alexander. And he got these dentafilms. These are self-developing X-rays, and placed them in there. And he put the cold reactor in there and exposed it. And he sent me these two. Well, actually, I got these in January the 15th, I think it was. I don't know what you can see. What can you see? Can you see anything? What I immediately saw are similar spots, and two of each of them. And I'm going to identify them here. They're pairs of spots. They're the same scale, just different orientations. I've got it over here as well. And what they are, in my view, in my view, they are solitons. And what you're seeing is it comes through. This is in water. I've got video links and stuff, but basically, if you get a plate in water and you push it, it creates a half soliton. And it lasts for a long time. And it creates a lensing effect, so the sun gets lensed away from the bottom of the pool, and you get these dark shadows. And so that's what I'm saying these are. sorry.
Аналогия с водой. Он показывает.
They're analog. Now, on that basis, without getting back to the SEM, oh, sorry, I'm just going to step in with this. This is at Suhas Ralkar's lab in India, and it's an ultrasonic device, and it's creating these hydrodynamic effects, and you're actually getting loops and so on, and they're merging and breaking up and disappearing and so on. It's another analog. So here's one frozen in time, and you can see it's wrapping round, and it's got a wave function on it, and so on. It's quite beautiful to watch these things. So I'd already seen that, so when I saw these two spots, I thought, here's our fuel, it's going through the alumina, it's going through the copper, and there must be some feature on the outside of the reactor that's the equivalent of what's causing the pull shadow on the X-ray. So here's our pull shadow from a solar tonneau pull, this is an X-ray. Okay, so this was my mock-up, and I thought, just for shits and giggles, I have a magnetic flux loop here. So I could not believe my luck. I literally went back to the SEM, put it under the SEM, and I thought, oh my God, I immediately saw it. We've got a pair here, we've got a pair here, we've got a pair here. Oh my God, and look, they're going up and they're going down. Exactly what I drew a couple of days previous. This is what I predicted you would see. This is exactly what you see, and I can even show you the paired matches. You can see they overlap. And in this case, the surface is CUO. It's not just that there's pairs of spots, they're actually pointing at the same angle, and they're almost pointing to something which doesn't exist. They're pointing to something here. They're pointing to something over here.
Ну да, он считает, что это проникает некое кольцо.
It's from this part of the
И оно
reactor.
создает пары, так? Пробивая пары.
Okay, so I'm thinking, are these triangles, because they're all triangular in shape, are they somehow related to this triangle here? And this, are they related? I don't know. So anyway, I went and looked at one of these triangles, and what I found is a cavity that runs through, and there was a slug, and this had frozen, in my estimation, at the speed of creation, okay? And whatever was going through that flux loop really reappeared in our space-time and went smash, and knocked that hole out. So you can disagree if you like now. So you're going to like this. This is all copper and oxygen here, nothing else. And guess what? This is for you. Calcium.
Well, you have 5 minutes.
Oh, really?
No.
Yikes. Okay, so this is to show north and south.
5 minutes reports and 10 minutes to a question.
I'll do the questions at the end.
5 minutes.
Tomorrow. Okay, it has a north and south pole. This is a cannon. So this is a thing. There's a cannon here. There's a one here. Comes out and in and out and in. And this is why you need to be close to the reactor. So when he was exposing his X-rays, he calculated that you need to be 12 to 13 millimeters to get the best focus. So you can see this is literally a cannon. And this is the ejector that came out into our space-time. And this has got high levels of zirconium in it. It's completely different from the rest of the material, the ejector. Okay, I can't do this in 5 minutes. This is outside of the reactor. These are counter-rotating vortices. So you imagine your flux loop here, and this is an effect on the quartz that's not, the reactor end was here. So whatever it was traveled out of the reactor and came to this position and did that and sat there and did it. This is a previous reactor, Lion 1, and I'm going to focus, it does this weird thing where it can have a complete separation between what it does. And this is another one, so you've got counter-rotating vortices, and then within them you've got one in here, and here, and here, and here. And this is etching the material through. So you have one flux loop here, and then you have a fractal component to it. That's a closer look. So the echo few processor, I've documented that well. This is what I was talking about with Shishkin, who was saying you need thin films. We were able to stop it. So this is the fuel. It's got a thin film. There's an air gap, not a very big air gap, and then some more polymer. And then under a laser microscope, you can see these pairs and so on with the sort of field, whatever around it. There might be just damage to the plastic, I don't know. But these are what I'm interested in, and there are lots of different kinds of tracks on it. This is in quartz of another one of the line reactors, and this is a perfectly width line, and Shoulders showed this boring through alumina. This is boring through quartz in my view. It's at least 8 centimeters long, this bore, and it changes direction as it goes, and as it goes it dumps crystals of different materials. So it's going eat, 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 eat. Here you've got a spiral and it's going even across this boundary. This is the cut line, and it literally goes to the whole length of the reactor didn't fracture. It got cut through. So it's like the active agent was eating its way down the length of the reactor. Now I've got this sample here with me. I asked the crowd, what can they see in this macro image, which I took with this lens here? I asked them, what can they see? Well, what they did tell me was this, and this, with a crater in the center. You see it here, and these are different elements. You have a crater where materials disappeared, and you have this. Now I predict, based on the line reactor, this will be rich in calcium, and what goes in the center is rich in heavy elements, like iron, and it is. That's what it is. So you have these things that appear spheres, and like I showed you at the beginning with the perfect cube from the Suhaus-Ralkar device, here we have a perfect dodecahedron. Okay, so I'm just going to show this. This is for Shishkin. This is a sphere this is a hole because it's cutting through the material. This is a sphere that's come out, but it's still got the shadow. So that was from a Hutchison sample. This is Shishkin. So you have your material being pulled in. You have it black, not there. There's holes in every one of those paw prints. And when it dies, it leaves the sphere. And that's what we have with these spheres, in my view. This is from this sapphire reactor. It's perfect for creating these structures. It has 2 planes. A large copper plate creates an electric field like that. You have a dome in the middle. It means you've got faster, shorter mean path. You can create your toroids. They put this tungsten probe into their reactor, and in like 1 frame, it did this. The tungsten probe disappeared, and it had this, what looks like a calcium deposit, with these spheres along the edge.
Now your time for questions.
Can I pass on the questions and do it later? I've got a bit of time to go. This is echo fuel. We have spheres around the edge of the echo fuel, and there are strange radiation tracks coming directionally off the spheres. I would argue that the structure that built the spheres was chucking out strange radiation, and when it collapsed, it dumped the sphere. This is on a Hutchison sample, and it shows the fractal nature. This was spotted by a crowd from my images. You've got a crater with a spot. You can't really see it on this one. But you have a spiral of spheres into the center here, just like that Schauberger spiral on the Ralkar sample. So you've got 6 spots around, and around the spot you've got spots like this. I don't know what that says. Yeah. So this is from Lion, and you can see a structure breaking up and bits of it going off. This is another one from a different Lion reactor, and this is in the quartz. This is in the quartz, the inside, outside. This is from one of your nuclear research labs, and you think it's something to do with plasma. You've got a 5-point star. This is Bostock. You've got the spot in the middle. This was from Shoulders, and all I did was contrast adjust, and you can see the spot in the middle and the spots around the outside. Each one can decay away. This is Hutchison. And this is very important. This is the shape, and I'm going to show you what that shape is.
Ну, это все вот следы кратеров, которые там все пытаются систематизировать, анализировать.
So this is a torus. It's spinning around, and it's also spinning around when it's spinning around. It has some effect on the field there, but this material here is being pulled in from here. Okay? Now, where's the evidence for this? I've already shown you, you can have multiple points on it from different researchers going back to the 50s. This is a 2-point galaxy. This has a clone of the base structure here and here, and it's spinning around this way. What does this tell you? The propulsion pull, i.e. the area in which it's pulling material in, is this one is flying out, perpendicular to the structure. It's eating material and it's throwing it out. And it's got left chirality. Okay? This one here has got 3 on it. 1, 2, 3. It's got the opposite chirality, but it's got a dome on it. And that's because it's going in. This is an exit wound. This is an entry wound. So you've got the basic structure with a spot. You've got fractal, which I showed you on the Hutchinson samples. You've got 2 and 3. Let's go for some more. This is on the changed CUO. And I spotted this. There's actually a 4-point here, and there's a 5-point here. And I've blown it up here. I hope it comes through at this resolution. So what I'm doing is I'm just taking the different elements that were identified and overlaying them. And that's where I want to stop. You've got your 2, which is actually a ring with 2 rings on it. So you've got the core fractal with a spot in the middle. That's the core element. You have another one here, and then you have 2 on it. Okay? And this is a 5-point one. You can actually see there's other ones interacting because you've got, it's not this one, but you've got a scar mark from where one went through here and another one went through here. So yeah, like I say, there's a 5-point there. So we got a 0, a 1, a 2. Sorry, you can't have a 1. You have to have it balanced. So it's at 0, 1. Now, after I did this and came to this conclusion, I was sitting there on a Wednesday in ICCF in America. It was a little tedious presentation. I don't know whose it was. I don't want to name him. Her, don't know. And I opened a book that was Kenneth Shoulder's key reference. And it was by Lafferty, vacuum arc discharges, about 30 years of research. It was published in 1980. And I couldn't believe my eyes. I absolutely could not believe my eyes. The book fell open at a page. It cost $180. There's only a few copies in the world. And there it was. They had this. I literally could not believe this.
Обратите внимание, на фотографии меняется вот состав, окраска вот это означает, вот купром сейчас, да? Смотрите, там.
He drew this and he's even parameterized it. And what did he do it with? He did that vacuum arc discharges, and he studied it over many years. It was published in 1976. He didn't have the ring on the base unit. He just had a spot because you can't see the ring. You only see the ring when it has the next level of fractal. Okay? And he never went beyond the basic fractals. So if I actually go in here, I've got the levels of fractals. Each one of these spots can be any one of these up to 1 million around it. So, but it has, Kenneth Shoulder says it has the same minus charge. So you can have one with 1 million on this spot and one with 1 on there, and they will balance. Because the mass and inertia is screened. So what I'm essentially saying, there is a black hole in the middle or a black hole analog. You need to chuck 22 micrograms, that's the Planck's mass, into that center. And this is something that Adamenko said in 2000, I think in 2006. He essentially found on some of his samples that he had these things where he fired the primary ion in a SIMS device, and there was no secondary ion coming off. More than that, there was no primary ion. It was eating the primary ions. So they turned off the photomultiplier or whatever, and they saw a glow, and it faded away with the decay. And he repeated it, and he repeated it. And then one of his workers saw that there was an irregular ring around the outside, and at specific points around that ring, they observed the same phenomena. I'm saying it's black holes that are supported with black holes around black holes. So this is the diamonds. Now this is really funky, because the diamonds get eaten, and they end up producing these spheres. You've got a sphere around spheres. There's spheres you can't see in this, sorry, but this diamond has turned into a tube. How does that work when it's only 800 degrees? So what you have, if I click these two, are what I call diamond miners. These are the active agents. And if you've seen those strange radiation tracks, which look like they're entangled, in my view, it's one of these structures that is not stuck in place like it was in the Hutchison sample, boring and staying there, or as it did on the Lion sample. The structure is going, it's moving, and each of the black holes around the ring are scratching out the path. So it looks like they're entangled, but it's just one structure that's moving around. These are similarly entangled. One of the crowd identified that several of these points are entangled on the bigger frames. And so it's converting the diamond into a heavier element as it's eating it. More interestingly, there's a whole sphere taken out of a diamond, not running along with the crystal boundaries. So the carbon goes and disappears from inside the reactor, but where does it go? This is really interesting. You're gonna love this. Basically, we're looking at this super glassy substance. Look, that's down to stupid magnification, and it's still no definition at all. We can't see anything, it's just totally glassy. But the funny thing is, I published this at the beginning of the year, and no one's picked up on it. I call it Schrodinger's cat. As you're firing the X-ray beam at it, every now and again, there's no carbon, there's no carbon, there's no carbon, no carbon. It's going to do it. It's going to do it. Honestly, it's going to do it. Come on. Basically, they explode and then they disappear again, and they explode and they disappear again. And so we go to a new sample area, there's nothing, it explodes and it disappears again. Explodes, disappears again. And basically the carbon is trapped in the black hole, and Scholder says this, it can stay in a conductor, of which Cu2O is probably one of the best superconducting-like materials you can have. It goes and sits in there, and when you shoot the X-ray beam, Scholder specifically said, when you add extra energy, you can make it blow up. And what it does is it releases what it had in its capsule. Now here's something really interesting. Where the diamonds have disappeared, now what I told you earlier, doped diamonds are the best electron emitter. This is important to the process. So we've basically got hundreds of thousands of, in his reactor, hundreds probably, of little shoulders emitters, okay? And the interesting thing is, it's not the sharpest point, it's the ones in a certain plane that's starting to do stuff to the nickel. What is it doing? Now, the operator for the SEM said, it's just melting, don't worry about it. And I said, no, take out the analysis probe, I want to go deeper. So we went deeper, and we went deeper. It's a nanoparticle of nickel, and that is just a nanoparticle of nickel. And I found one paper by a very extremely methodical and precise lab in South Korea that's managed to create spheres on their own like this, perfect minimum energy crystals. Bearing in mind, this is just to slap it together in your bedroom with parts off eBay experiment, no vacuum lab or anything. And you can go in right close. I mean, this is stupid. This is 200 nanometers. So these are small structures, and if you had noticed, they're actually got their shape. The interesting thing is they have what I call fleur-de-lis coming off the target points. So this is extremely high resolution. I'm going to pop into it so you can have a look. I'm going to come out, I'm going to zoom in like this.
Я еще смотрел, думаю, как он
So-
управляет действительно.
What I want to show you is
Ну, всяких-
how the crystals are flowing towards the spheres in every direction. This is called Zener pinning in crystallography. But what's different about these compared to this? What's different about it? Spot anything? It's much darker. Why is it much darker? Now I'm going to go over here. What's going on with this? What's that?
Вот за
So if you know your SEM, dark means lighter and light means heavier. So this isn't just a pure nickel crystal. It's dumped something at this node, which is a heavier element. And the other one it dumped, which is a lighter element. But still they had the pull to pull it all together.
Ну, это его телепортация.
Это при движении этих самых примесей.
Okay, so what I'm saying is that this structure can have any number of things around it, which can all be black holes containing any amount of matter. If you know what a black hole can do, you know where your excess heat's coming from. You also know where your excess cold is coming from when it breaks. You also know where your electricity is coming from. You also know why it sucks in electricity.